Okay, my name is Aaron Wallace. I'm a master's student at Virginia Tech University, and for my master's project, I'm trying to do a self-study, self-learning um, of how to use the SPARTA program. That is an open source program that's the Department of Energy funded, and Sandia Laboratory, I believe, is how it's pronounced, produced. So it being an open source program, it's a little more confusing to use. It doesn't have the graphical user interfaces and all the simplicity that a lot of commercial programs have, but it's a very capable program that I've found. And so this will be my first example. I'm going to be doing at least three examples. So this first one comes from chapter 12.2 of Bird's book, which is one of the texts that I guess is fundamental text for the direct simulation Monte Carlo method. So in excuse me. So in section 12.2, he is using his original Fortran code where he's creating the whole process to determine the viscosity coefficient of argon, and he's using it in, I guess the simulation is Couette flow, where it's two parallel plates, and the top plate is moving, and then he's performing his calculations and comparing it to experimental data. All right, so we're going to perform the same simulation in Sparta, and I'm going to walk through the process of doing that and the different files you need. So first thing, let's talk about um, so all these simulation parameters are given inside of the text of 12.2 of Bird's book. It's copyrighted, so I don't want to show it. But I ever talk about it's quasi 1D. There's only a change in one direction. Sparta won't let you do 1D programs. We'll talk about that in or 1D simulations. We'll talk about that in a minute. So the two walls are a meter apart between the top and the bottom surface. The lower surface is stationary, and the upper surface is moving at 300 meters per second. And the surface temperatures are kept constant at 273 degrees Kelvin, and the initial gas temperature is 273 degrees Kelvin. Inside of Bird's text, he talks about how you can either initialize the gas at the free stream or the 300 meters per second, or you can initialize it as stationary. I tried it both ways. I liked my results better with initializing as stationary, and that's what I'm going to show here, but I'll show you where you can make that change. The gas that we're using is argon. This is the first example in the section in the 1D examples because the simplicity of it, because it's a monatomic species and it's not a mixture, so it's only one species you have to worry about and have collisions between. All right, he discusses the number density as being 1.4 e to the 20, and he says that the collision model he uses is the variable hard sphere model. Um, he talks about the mean free path and the Couette number, and then his time steps are 2.5 e to the negative 6. He said he took 40,000 transient time steps. That's how long he assumes it takes to get the steady state, and then he throws that data away. We used 50 in Sparta, 50,000, and then the steady state data collection time steps, he said 110,000 in his, and I used 100,000 in Sparta. Same total time steps. Number of grid cells, 200. So he breaks up that 1 meter into 200 different grid cells. The number of simulation particles, he used 10,000. And the number of particles per cell, he used 10,000. 50 particles per cell. And so I simulated and did the same in Sparta. All right, so one thing about Sparta is it is only for Linux systems, so you could use the Ubuntu or in WSL, or what I've chose to do is get an Oracle VirtualBox, and then I can get installed Linux Mint, and that's seems to be a little more similar to like how Windows operates, so it's easier for me. You still have to use the command line in it, but the file um, organization is easier for me to see and understand. Um, so here you'll see where I've got Linux Mint, and there's a whole lot of installing Sparta and setting up the WSL. There's a lot of videos out there. If people really struggling with it, I can try to help, but I was able to find enough videos and information on the internet to get, Sparta running on this with MPI, and like I am not a tech whiz by any means. All right, so let's talk through the different files that you're going to need to run this simulation. In this simulation, we'll have a total of 3 files that go in. These are all come later, the log and these grid data ones. We'll discuss those, but you have a species file, you have a collision file, and you have an input file. For this project, or this simulation, since we're using the upper and lower boundaries as surfaces, we don't have to have a surface file. If we had a surface somewhere in the middle of our domain that wasn't part of one of the boundaries, we would have to have another file that's a surface file, and I'll discuss that, I believe, in the third example I'm going to do. All right, so let's start with the species file. So this file eventually gets read into the input script, but it's where you describe the species that you're using and all the different parameters related to it. And it's laid out where the first is the ID of the species, and then you have the molecular mass. Nope, you have the molecular weight, then you have the molecular mass, then, as you can see, all these other ones, rotational degrees of freedom, rotational relation, vibrational temp, species weight, charge. You do not have to include all these if you do not plan on using them. The rotational degrees of freedom for this is 0. I found that it's written in the Sparta manual, which I can show you right here. You can look, and it's 518 pages. It's very in depth. Everything you need to know is in there. It's just, it can be a challenge to dig through it and be patient with it. We'll open it up and look at a couple things here in a minute in there. But so it describes that this is the case. For monatomic it's 0, for diatomic it's 2, anything else is 3. I didn't include any of these other rotational relation, vibrational, or charge. The species weight is included because this is how you can weight the simulation versus real particles. If you put it at 1, then inside your input script is how you'll weight these things. You have to turn on rotational and vibrational energy exchange inside of the input script for any of these other aspects to even be included. So for this simulation, they're not going to be necessary. All right. So then this is our collision script. It's naming it VSS causes it to pull up this different type text file. It really doesn't matter. But here's where we got the VSS or or VHS collision model parameters. These parameters you put in here determine whether you have a VSS or a VHS model, collision model that you're using. So first thing, species or species pair. So here we're looking at argon. So this is an argon to argon collision. And so that's the only types of collisions that will be possible in this simulation. So that's the only line that we have in here. All right, so then next one is the diameter, and then you can go to either table A3 for the VSS parameter or A2 if it's VHS. So this is the number from table A2 in Appendix A of Bird's book. Omega, you can go to table A1 in Bird's book in the Appendix A, and it's the same for the VHS or the VSS. All right, Tref is from either table A2 or A3 of Bird, depending upon if you're VSS or VHS. And then alpha, that's the scattering parameter. if you're doing VSS, you got to go to table A3. If you're doing a VHS model, alpha is always equal to 1. And so that's why alpha is 1 here. It's important to pay attention to this stuff because if you put the VSS parameter in here, your results will be skewed greatly from what Bird did in this section. All right, so next we get into the input script. And so this is what Bird said in section 12.2 that the measured number was for the viscosity coefficient of argon at 273 Kelvin. So that's the I just put that in there. That's the number we're roughly comparing to. You see here, I'm going to have 50 transient steps that are discarded. That's a total of 0.125 seconds, and then our steady state, we're going to take data over 0.25 seconds. Total of 150 steps, total 150,000 steps. So this initialization, this is where you initialize SPARTA and just tell it, hey, I'm getting ready to run a problem. Here's where you determine the dimensions. SPARTA, you can either do 2 dimensions or 3 dimensions. There is no 1 dimension selection for this. So to run that's why I say it's quasi 1D, and to run it that way, you have to adjust your boundary, your grid to where it's only 1 grid wide. All right. And so here we go into our boundary conditions, and then when we say our boundaries, we got to determine what kind of boundaries we have. And this is the key to this part, because since we don't have a surface coming in, a surface file being read, we have to tell SPARTA that we are going to be treating the upper boundary and lower boundary as surfaces. And so here's our selections for this boundary. So first is X, Y, Z, and then so we're going to say P is periodic, R is spectral reflection, A is axisymmetric, and S is treat boundary as a surface. And so we're saying here for X, we're going to say it's periodic, and then we're going to treat Y as a surface, and then P, then Z, we're going to treat as periodic. And periodic means as something enters one side, it leaves the other, and vice versa. All right. So we've just told SPARTA what type of boundaries we're going to have. And now, since we said the Y boundaries are going to be surfaces, we have to describe these surfaces. So we're going to say one surface is a surf collide, and we're just calling it surface 1. That's just our variable for that. And then we're going to say it's a diffuse surface, the temperature of the surface, and then this, when you use diffuse, you have to give it a temperature, and then you have to give it a ratio between 0 and 1. 1 means it's totally diffuse. 0 means it's totally spectral. And so in this case, we're using 1 because it's going to be a totally diffusive. And this is basically, I believe it's the percentages of, or the ratio of spectral versus diffuse. So if you're saying 1, it's saying all of the collisions are going to be diffuse. If you have 0, it's saying all the collisions are going to be spectral. And if it's 0.5, it's saying it's half and half. And so, okay, so let's move on. Then we have our other surface, which we're saying is surface 2, or and it's going to be diffuse, same with that, but we're going to translate that surface 300 meters per second in the X direction. So that means this is what's going to tell our upper surface to move to the right at 300 meters per second. All right, so then you got to use the bound modify command, and we're saying our Y low boundary is going to be collide 1. So that means our lower surface is going to be the one that's not moving, stationary. And our Y high collide 2. So that's saying our upper surface is going to be 2, which is the one that's moving. All right. And then once again, if you go into the manual, if you click this, you go to the individual commands, you can look at all these and work your way through how to enter these commands. Using that in the examples, it is a challenge to get it the way it wants it. All the information is in there. It's a challenge. It's detailed. Okay, so where were we? Let's go back here. And so here now we're going to define the domain geometry. And this is just basically like telling our box, like defining the box that the simulation is taking place in. And so here's where I picked the value for the dimensions of the cell width in the x direction. And so this is going to be like one cell width because we're only going to do a quasi 1D problem. In the y direction, we're going from 0 to 1 meter. And in the z direction, I'm going negative 0.005 to 0.0005. And when you read through Sparta, when you define a problem as two-dimension, you have to take this z dimension and you have to split it evenly on both sides of the zero. That it always runs it as if it's 3 dimensions, but it just says, okay, yeah, we're going to make this just a one width. All right, so that's how I did it for this. This volume this dimension right here does come into play if you choose to define the number of particles you have by fnum, and so it's not totally irrelevant, but it's part of what you work through. All right, so next we're going to look at our grid. This is where determining how many grid cells we have. We're saying it's going to be 1 cell wide in the x direction, 200 cells tall in the y direction, and 1 cell wide in the z direction. Then we balance the grid. There's information inside of Sparta that explains like every one of these commands. This seems to be the most normal selection is to use the RCB cell. Just look through Sparta and determine if the manual and determine if that's what you want. All right, next we go down to our gas and species mixture. All right, so this is where we're going to tell Sparta to pull in that other file that we made. So we're telling it the species that we're going to run inside of our simulation comes from the AR species file, and we're using the parameters for the ID AR. So that tells it to pull in the information that we put in this species file under the ID name AR. All right, next we're defining our mixture. This is where if you did have a mixture, you would put the ratio of each species. But here we're saying our mixture is gas. We're saying it's this AR, and we're telling it the temperature of the mixture and the velocity of the mixture that's just initialized. And so we put the temp at 273, and then vstream command is where you can give it a initial velocity. And this is where if you wanted to start with the gas moving at 300 meters per second, you would change this to 300 meters per second in the x direction, and that would give you that. All right, but like I said earlier, we're doing stationary, so the vstream is initialized at 0. Initializing it stationary, I believe it could be totally left out, but I have it in there. Next, we have the particle weighting and initialization. This is where you determine how many particles you're going to have in your simulation. Bird talks about n rho is equaling 1.4 e to the 20. You take n rho, the number of cells you have, the number of particles you want in each cell, and the volume of the cells, and you can figure out fnum. And this is really close to the number that you would figure out that would give you 10,000 particles per cell. Particles for the simulation, but I went ahead and just force-fed it 10,000 particles. So when you use this create particles command, you're telling create particles from this gas, and then you're telling it you want n particles, and then I'm telling it how many. And then if I were to put a 0 right here, it would actually do the calculations from fnum and n rho and tell you how many and it would initialize it with those particles. So it'll get really close. It'll be a few particles off, but it'll actually, if you do the calculations, you can put 0 here and you will get the same number of particles as if you put 10,000 here. All right. So next, you got to tell it what your collision model is going to be. I believe in Sparta, you have to just call VSS. Where your variable hard sphere model is defined is inside of this file, which is AR VSS. So that's where it determines what parameters are used. So you're saying you're going to use collide VSS. It doesn't mean it's a variable hard sphere model you defined it as a variable hard sphere model inside of this file. So I know that's a little confusing, but just look into that in Sparta if it's confusing to you. But this ar.vss, where we discussed earlier, is where you define what model you're in. So I'm telling it to use the gas, and then it's pulling in that file that we created earlier for the collisions. All right. So now we get into computing properties during the simulation and after the simulation. If you look up compute, this is one of the more challenging parts, because you got to figure out what you need in your post-processing, what you're comparing to. As you can see here, I'm pulling out velocities, mass density, number density, temperature, pulling temperature again. Like, these temperatures are not always the same in the different sections. Then energy flux and momentum flux. So if you go to, once again, go to the manual and go to the compute command, you'll see these are all the different kinds of computes you can do in here. And there's a bunch of them related to surfaces that later on in some of the other examples we'll use. And then a lot of them are related to the grid. But just here, for example, if you click grid, here I tell it compute, and I'm calling this group of computes gcomp. And I'm saying we're going to use the grid command, and I'm saying all the grids, and then I think this means all X and all Y. But then when you go to this, it tells these are all the different variables you can compute. And Sparta will give you results for on a grid basis. And I believe it's the average in that grid cell. All right. So those are all the different ones. There's energy flux, momentum flux is discussed. It depends on what you are comparing to or what information you need. All right, next you got to go to the fix command, and this is how you average over time steps. So what we're saying here is we're going to fix. So we're looking at gfix. So we're calling what this fix produces gfix, and then we're saying we're going to do the gfix on the gcomp. So what we're saying is we're going to come up here, we have this information, and we're going to average that information for all of the grid cells, and we're going to do it for every time step, and we're going to do it, the average is going to be over 500 time steps, and it's going to happen at time step 500. So every 500 time steps, this thing is going to look at the 500 previous time steps and create an average. If you can do this 10, 100, 1000, and it'll look at every 10 time steps, and it'll take like 100 of those that happen every 10 time steps, and on the 1000th time step, it'll average those. And then we go down to where we dump, and we're saying we're going to do a grid dump on grid all, and every 500, it's going to dump the all this data into a file that's going to be called grid, and then the time step number in DAT. And this is where it's telling you what it's going to dump. It's going to dump all this stuff here that has averaged everything for all of these variables. And when you have the little, you can call these out individually if you want them, but when you have the little star in there that basically says, yeah, for FH fix, give me all of this, give me all three of them. All right, and for M fix, it's just one here, but so that's how that works. All right. So then we look at statistical output. This just as your command line is, as the program's running, it's going to show you every 500 steps. It's going to push this stuff out. It's going to tell you the steps, the CPU usage, number of particles, number of attempted collisions, number of collisions, etc. And so that's just a way for you to kind of, like, as you're running the simulation, look at the window, see if the simulation is progressing as expected. If you're running the simulation and all of a sudden the third column over says 0, that means you have no particles. That's not your simulation isn't working. Or if you're looking here, you got no collisions, that tells you your simulation isn't working. Because this simulation takes 2 to 3 minutes, but some simulations might take hours. All right, next here we got where we're telling it the time step. Just as Bird had, we have the same amount, 2.5 e to the negative 6. All right, so then we go into the phases. So as of now, we've described our simulation. Now we got to actually run our simulation. So what we're going to do is we're going to run our simulation for the transient period, and then we're going to run it for the steady state period. And we use this undump command, I guess, just to get everything cleared up. And then we're going to run this simulation for, so here's where we're just telling it not to dump files during the transient period. So we described it all up there, and then we're saying, okay, but don't do it during this transient period because we're not concerned with that. All right, so we're going to run it 50,000 time steps here, okay? So after we get through with that 50,000 time steps, Sparta's going to go back through and it's going to say, okay, now we're going through and we're going to enter a different phase, and we're using these unfixes, which I don't necessarily know. Like, I think there's a way to simplify it and not use this section, but I used it. I'm basically going back through and saying, okay, get rid of the fixes we had earlier where we did our averaging, and then we're going to refix them. And then what I've done here is I've done a running average. And so, like we discussed earlier, this thing is going to basically do these calculations it's going to, like, the original fix was basically doing an average over 500 time steps. Once it takes that average, it's going to make that a running average. So as we go through these 100,000 total time steps, every 500 time steps is doing an average of the previous 500 time steps, and it's making that part of the running average. And you could actually increase this to 100,000, and you would get running average, just an average over the whole time step. But you'll find that if you do that, your simulation really slows down because it's having to store all the data for these five. Like right now, it's storing all the data for 500 time steps. Then it does the calculation, and it just has one set of data, like one set of numbers that it's storing, and then it does another 500, and then it averages those two together. And so this allows it to move along at a much quicker pace. All right, and see, here I'm dumping these grids, so I'm not worried about dumping these every 500 time steps. I'll just dump it every 50,000 time steps. That way I don't have, 100 and something files that I have to, navigate through. And so when it's all said and done, I believe I'll have one at 50,000, which won't have data in it, and then I'll have one at 100,000 and one at 150,000. Time steps, and the one at 150,000 time steps it'll be the running average of these 100,000 time steps. Okay, so I think that pretty much sums up all the input script, the species script file, and the collision file. So if we go back to here, I found that you can see this is where I've ran it before. Sparta always puts out a log at the end, and then these are my data files. You see that I've told it to, don't give me anything at the transient period, so that's why that's 0. And then this is my final results, and we'll get to that in a minute. What we want to do is go ahead, and I just choose to open the terminal from here. And so this just puts me in this directory. And then basically here's how you run Sparta, and there's videos out there that walk you through one of the Sparta examples that'll help you understand all this. But we're basically telling we want Sparta to do an MPI run. I'm saying the number of processors I'm going to use is 2. You can change that, or you can get rid of that altogether, and it'll use whatever available processors are in. I found I have pretty good speed for these simple problems of 2, and I'm working through the virtual box, so I don't really know what's available. All right, so then you're telling it where to go find the Sparta MPI file. So you're saying hey, go to this directory and then this directory, and that's where this Sparta MPI is. And then we're saying we're going to run this in Couette bird cell. And that's what I've just got my input file named. You can name it in whatever, and it'll go through. All right, so you'll see it initialized it. It created the particles, and then talks about the memory usage per CPU and stuff. And then you'll see this is that stats part we were talking about. These are the step numbers on CPU. These are how many particles I have. 0, there's no collisions, no attempted collisions. And then you can see, and one thing you want to see is you want to see these collisions and all be reasonably stable. If they're growing, or if they're shrinking, if you got a problem. You see it just switched over into doing the steady state. That was all the transient up here, and now it's switched over to doing the steady state part. And so we actually are going to be putting out information here in just a second. Let's see. I'll just pull up this one. Let me see if we pass that. Let it run just a second longer, and then I'll pull up the 100,000 just to walk through what the file looks like. Okay, so it's rewritten this since we've ran it. All right, and so you'll see that it talks about the number of time steps, number of cells, and it tells you what your boxes are like. And then you get up here, and these are your cell numbers, where it's at. And then you start looking here, and you'll start seeing like these are all these fixes that you put in here. And so it can take some work to understand what you're getting here versus what you're getting, or what you put into your input script. And so you just have to take your time, look through these columns, and look back at your input script and just see which ones relate to which. All right, so I made a small, I guess not a small, but I made a comparison script to compare the results to what Bird had. And also for this problem, I wanted to learn how Bird's programs were working, so I translated his original Fortran information to MATLAB and ran the program and took the data from that. This program takes 2 to 3 minutes to run in SPARTA. In MATLAB, it took, I think, probably an hour and a half, possibly. And so when I pull this up, this is going to show the results of both. And so we can see here that our heat flux from SPARTA is looking very similar to the heat flux from our MATLAB translation of Bird's Fortran code. The same for our shear stress. Mass density is looking very similar. The temperature comparison inside of the domain is looking similar. You can see there's actually like some temperature slip there. And then our velocity comparison is looking very similar to what Bird got in his using Bird's original Fortran code translated to MATLAB. You can see the velocity slip on the walls, which makes sense also. So you know that the physics is working as it should. All right, so here's where I've done some comparisons. So we start looking down through there, and like our velocity gradient is real similar to what Bird stated his velocity gradient was, and what my code, my MATLAB code produced. Start looking at the temperature; it's all really close. The density is all really close. Shear stress, all really close. One thing we can see is that the mean pressure is that SPARTA produced is very close to what Bird stated in his text, which is 0.54 or 0.55 PA. So that just lets you know exactly like how low the density actually is if the pressure is only half a Pascal compared to what we have here at the surface of Earth. Start looking at the slip on the walls. The main thing that we were looking at for this project was the viscosity coefficient. And you can see that here's my SPARTA viscosity coefficient, and then here's what Bird reported his was. This is all really close to what the measured value was that Bird was comparing to. So as we can see that SPARTA has done a good job on this section 12.2 of Bird's book of reproducing the results. And it was a good first step for me for learning how to use SPARTA. And if you have any questions or any comments, feel free to put them in the comments. And if I get to it, I'll try to answer it if it's something I can answer, or we can have some discussion. And like I said before, my name is Aaron. I'm a master's student. I'm just trying to learn through this final project, and I appreciate you watching, and I hope it helps somebody. Thanks. Bye.